These are some sample questions that deal with the first two lessons that we've gone over in Unit 4, namely collision theory and the factors that affect reaction rates. So we're just going to go over some of these questions together. Hopefully this will help you with your homework, help you with the test, hopefully get a better understanding of, again, those three things that affect if a reaction is going to happen and the four things that determine how fast the reaction is going to go. So question number 1, we can see a balanced equation up there. We can see that they did two different experiments. And in one of them, the important part right here is that we can see that the concentration of hydrogen was higher in the second experiment than in the first. Okay, and that's all. We see the temperature is the same. Let's go ahead and read the problem here. The initial rate of formation of CO2 from a chemical reaction represented by the equation above was studied in two separate experiments. We already see that. The table above provides the experimental conditions used. Both experiments are carried out with finely powdered samples, so they're telling us the surface area is the same, of the solid and 50 milliliters of HCl. So even though the concentration of HCl is different, the volume is still 50 milliliters. Okay, but the 50 milliliters of in experiment 2 is 2 molar hydrochloric acid, whereas in experiment 1, it's only 1 molar. Now again, notice that instead of using HCl, they just do H+. And why do they do that? Because again, many times on the AP test, they just show the net ionic equation. So in this case, even though it is HCl in the equation, you're just seeing H+ and H+ here because they're just showing the net ionic equation. That Cl- canceled out. So which experiment will have the faster initial rate? So this is not a question of will the reaction happen. They're saying it's going to happen. It's a which reaction is going to happen faster. Well, based on what we've learned, there's four things that affect how fast a reaction can go. And the first one was concentration. The greater the concentration, the faster the reaction goes. So we know that in experiment 2, the concentration of hydrogen is greater. And really, that's it. That's all you got to know. Okay, so the answer is C. CO2 will be formed at a faster rate in experiment 2 because more hydrogen ion particles can react per unit time. Okay, and again, if you look at the other answers, the rate of formation will be the same because the mass of calcium carbonate is the same and the volume's the same. That's great, but again, think about what you've learned. It's concentration, not volume, that affects how fast the reaction goes. Okay, it'll be the same because the surface area and the average kinetic energy. Again, true that the surface areas are the same and the kinetic energy are the same, but there's other things that affect the rates other than just the surface area and the kinetic energy, namely concentration and catalysts are the two things they don't mention in answer B. Okay, and then CO2 will be formed at a fast rate in experiment 1. A, that's wrong, because the proportion of CaCO3 solid particles to H+ will be greater. That's just simply not true. Okay, question number 2. Here's an equation here. What effect will increasing the hydrogen ion concentration, and I don't know if we make sure we understand that when you see something in square brackets like that, whether it's H+, whether it's HC2HO, if it has square brackets, that means the concentration of whatever in, and it's always measured in molarity. So when they have that, they're saying what effect will increasing the concentration of hydrogen ion at constant temperature have on the reaction represented above? Well, again, you are increasing the concentration of one of the reactants. And when you do that, that makes the reaction go faster. So the activation energy will increase? No. Again, changing the concentration does not change the activation energy. Activation energy will not decrease. The frequency of collisions between hydrogen and ClO- ions will increase. And again, when you increase the concentration, what does that do? That increases the frequency of the collisions. Okay, answer C is correct. Answer D we haven't even talked about yet. Don't worry about what answer D means, but we will get to there. Okay, but that obviously is also not true. Okay, question number 3. The gas phase reaction between A2 and B2 is assumed to occur in a single step. 2 experiments, and again, there's some of this stuff that comes up later on in Unit 4, but is not important to the question now. So the fact that it's a single step doesn't mean anything for this problem. 2 experiments were done at the same temperature inside rigid containers. The initial partial pressures of A2 and B2 used in experiment 1 were twice the initial pressures used in experiment 2. So the pressure in experiment 2 is twice as high as in experiment 1. So why is it higher? Either the volume was half as much, or they put more stuff in there. There's twice as many particles in there as in an experiment 2. So we know the greater the pressure, that's also another way of measuring concentration. The greater the pressure, the greater the concentration. Because remember, concentration is moles over liters. So if you increase the pressure, what you've increased is you've either increased the number of moles, and that makes the concentration greater, or you've decreased the volume, right? By lowering the volume, that also makes the pressure go up. In both cases, the concentration increases. So we know that experiment 1, because the pressure is greater, that there's a greater concentration, that the reaction in experiment 1 should go faster. Okay, so which statement provides the best comparison of the rate of formation of AB in experiments 1 and 2? Okay, right away, same. Okay, it might be right, but for right now, I'm thinking that experiment 1 is going to go faster. The rate of formation of AB is slower. Nope, I don't think that's either. Okay, C and D both say faster, so I'm going to focus on those two for right now. The initial rate of formation of AB is faster in experiment 1 than in experiment 2 because at a higher pressure, the collisions between the molecules would have been more frequent, increasing the probability of a successful collision. I like that, okay? Increasing the frequency of the collisions, that's why when the pressure or the concentration goes up, the reaction goes faster. Okay, let's see. And then in answer D, at a higher pressure, a larger fraction of the molecules would have the minimum energy. Again, basically it's saying that you're giving the molecules more energy. Okay, if you increase the temperature, D would be correct, but you haven't changed the temperature. Raising the temperature would now give a larger fraction of the molecules. Okay, this is 100% referring to temperature. Okay, and that is not correct. So C absolutely is the correct response there. Okay, and again, guys, these are not your homework questions. Your homework questions are completely different from these. Hopefully these will just help you with them. Okay, number 4, which of the following best helps explain why an increase in temperature increases the rate of a chemical reaction? Does it lower the activation energy? No, it does not. Only catalysts do that. Again, higher activation energy, no. Okay, at higher temperatures, every collision results in the formation of a product. That word every is real tough. Remember when we draw that curve and we say, here's the activation energy barrier. Okay, again, here's your particles that have enough energy to overcome that activation energy barrier. A lot of them still don't. So to say that every collision results in the formation of a product is a no. But at higher temperatures, high energy collisions happen more frequently. And again, they hit each other more often and with more energy. So answer D is absolutely correct. Okay, number 5, factors that affect the rate of a chemical reaction. So again, what makes a reaction go faster is frequency of collisions. Well, frequency of collisions depends on concentration. So absolutely, that's a yes. The kinetic energy of the collisions of the particles, which is basically, again, the temperature. And then number 3 is orientation. The only one they left out was catalysts. Okay, and yes, all 3 of those are absolutely factors that affect the rate of a chemical reaction. The correct answer has to be E. Number 6 says the reaction between NO and NO3 is represented by the equation above. Which of the following orientations of collisions between NO and NO3 is likely to be effective? Okay, so look at that reaction. Notice you have an N and an O, and you have NO3, but then you have NO2. Okay, so again, you'll notice in the answers here, they're showing the orientation of those molecules. So if you're going to turn NO into NO2, okay, is it going to be NOO or is it going to be ONO? Okay, and hopefully you realize that the oxygen is going to form that bond there with that nitrogen, not with the other oxygen. So we need this nitrogen right here to collide with one of these oxygens here. So let's look at answer A. And answer A, and again, they show O is the open, N is the darker one, and O is the open one there. Okay, so this is showing an O hitting another O. Okay, that's not going to produce. Notice here that if this oxygen here comes off, notice you're left with O, N, O. Okay, and so it has to be, so that oxygen here has to hit the nitrogen side, not the oxygen side. Okay, so here, this oxygen again is hitting the nitrogen, it looks like. Again, that's the nitrogen isn't breaking off. One of the oxygens, one of these outer oxygens is breaking off. Okay, here the nitrogen's hitting the nitrogen. Again, we can't have the nitrogens. The nitrogens aren't forming a bond. They're still separate. Okay, but here we see the nitrogen on this one is hitting the oxygen here. That is oriented the correct way. That will allow that to break off and form NO2. Correct answer is D. Okay, number 7, we can see here's a Maxwell-Boltzmann graph. And we can see here that temperature 2 is clearly at the higher temperature. Okay, it's got, again, more particles that have enough energy to overcome that activation energy barrier. Okay, based on the graph, which of the following statements best explains why the rate of disappearance of NO2 are different at temperature 2 and temperature 1? Well, again, I think we probably just said it because we're at a higher temperature and more particles have enough energy to overcome that activation energy barrier. Okay, let's see. It says NO2 is consumed in A is consumed at a faster rate at temperature 2 because more molecules possess energies at or above the minimum energy required for a collision to lead to a reaction compared to temperature 1. I really like that answer. Let's check the other ones and just to make sure, but I think A is the correct answer. Okay, in B, the molecules have a wider range. Okay, we never talked about a wider range of energies that affecting the orientation. Again, think about what you've been taught. Okay, you've never been taught anything about a range of energies which affects the orientation. Okay, letter C. Fewer NO2 molecules have a relatively high energy at temperature 1, which favors collisions between molecules rather than between the molecules in a container, leading to a faster rate of no. And D, more NO2 molecules have a relatively low energy at temperature 1, which increases the number of effective collisions. Again, that doesn't make any sense at all. At the higher temperature, you would have more effective collisions. Correct answer is A. Okay, question number 8. The reaction represented above occurs in a single step and involves the NO and NO3. So kind of like that earlier one with NO and NO3 about the orientation one. A scientist correctly calculates the rate of collisions between NO and NO3 that have sufficient energy to overcome the activation energy. So it's like, okay, basically they're saying forget about activation energy. But then they're saying the observed rate is actually only a small fraction of the calculated collision rate. So it's saying the rate is actually a lot lower than what this scientist has calculated it to be. Why might that happen? So again, they're colliding with enough energy to overcome the activation energy. What's the one thing that's missing about what makes a reaction happen? They have to collide with enough energy, and they have to collide with the correct orientation. Okay, and that's what's missing there. Okay. Let's see. The energy of collisions between these particles is frequently absorbed by the collision with a third. They did use the word collision there to try to throw you off. That's not talking about orientation, though. Okay, the two reactant particles must collide with particular orientation in order to react. Absolutely, B is correct. Okay, the activation energy is dependent on the concentrations. That's not true. The activation is dependent on the temperature. Again, not true. Neither of those two things cause the activation energy to change. See how many times I brought that up now? That's a big, big misunderstanding that students think that temperature and concentrations can cause activation energy to change, and they don't. Only catalysts do. Okay, so question number 9 shows you here's a slow reaction, here's a fast reaction. Why is this one slow and this one fast? Let's look at our answers here. The only factor determining the rate of step 2 is the orientation of HI and ICL polar molecules during a collision, but it has a negligible effect when H2 and ICL molecules combine. Did we ever talk about polar versus nonpolar when we're talking about orientation? No. They just have to be oriented the right way. Okay, letter B, the amount of energy required for a successful collision between H2 and ICl, so that's step 1, that's the slow step, is greater than the amount of energy required for a successful collision between HI and ICl. Okay, and that's our fast step. Okay, that actually makes sense. If the first step requires more energy, so that activation energy, basically remember to get over that hump, if it's higher versus, so this, let's say this is step 1, and then in step 2, it's basically like this, much lower, okay, then absolutely, if it takes more energy to get up over that activation energy barrier, that absolutely can be a reason why that reaction is slower. Okay, the fraction of molecules with enough energy to overcome the activation energy barrier is lower for HI and HCl. That would make it faster, so no. And then D, the frequency of collisions is greater. Again, the frequency of collisions, if the temperature is the same, So D is also a no. So B is the correct response there. Okay, and then our last one. Which of the following statements can best explain why an increase in temperature of 5 to 10 degrees Celsius can substantially increase the rate of a chemical reaction? Again, when you increase the temperature, what do? The molecules start moving faster. They hit each other more often. And as they hit each other more often, they're also hitting each other more forcefully. So the activation energy is lowered. Again, no. Temperature doesn't do that. The number of effective collisions between reactant particles is increased. I like that. Let's see what else we've got. Well, the other ones we haven't talked about. So we are going to learn about delta G and delta H later on this year. And we haven't talked about the rate of reverse reactions either. So none of those could be correct, or I wouldn't have given you that problem. But B is absolutely the correct response on that.